In this lecture, I'd like to work through a few examples involving circular motion. Let us say that we have an object which is at an initial angular position of 45 degrees with respect to the x-axis. So here's our x-axis, and the initial angular position of the object theta I is 45 degrees as shown here, and that object starts at rest, so omega naught is 0 radians per second, and then it speeds up for half a second to 1540 revolutions per minute. And after reaching that value for angular velocity, it continues at that constant RPM for yet another half a second. And let us say we're interested in finding total displacement of the angular displacement of the object at the end of the 1 second period, that is this half a second here plus this half a second here. Now remember, for the first half seconds the object was speeding up, was winding up, and for the second half second it was continuing at constant angular velocity. Before I solve this problem, let me say that what we learned in the case of linear motion is also valid in the case of circular motion. In particular, we learned that velocity final is equal to velocity initial plus acceleration times delta t, and displacement delta s is equal to initial velocity times delta t plus 1/2 of acceleration times delta t squared. These are the kinematic equations of motion, of course, and that velocity final squared was equal to velocity initial squared plus twice acceleration times displacement. All these are valid, of course, if A is constant. That was the golden rule. Now in the case of this is our linear motion. In the case of circular motion, the analogous equations, kinematic equations, become final angular velocity is equal to initial angular velocity plus angular acceleration times delta t, and angular displacement is equal to initial angular velocity times delta t plus 1/2 of alpha delta t squared, and omega final squared is equal to omega initial squared plus twice alpha delta theta. These are the circular kinematic equations, and the condition that one needs to make sure is satisfied is that alpha is constant over delta t, the period delta t. Now for uniform circular motion, alpha was equal to 0, as you recall. Therefore the equations at the top become omega f is equal to omega I, i.e. the angular velocity doesn't change in uniform circular motion, and delta theta takes the simple form of omega I delta t, and well, these are the only two relevant. The third equation is also omega f is equal to omega I. So for uniform circular motion, alpha was 0, of course. So going back to the problem at hand, you can solve this problem by applying the circular kinematic equations, the ones that I have here, of course twice, once for the first stage of motion, and and then repeat the analysis for the second stage of the analysis, find the respective angular displacements and then add them up. Or you could simply use the graphic technique, that is, plot angular velocity of the object versus time, right? Omega versus t. We know the object starts at rest and then it continues, it winds up at a constant rate to 1540 RPM, so that's our straight line going up, straight line, constant slope, and this slope here of course is our alpha, and then it continues at that constant RPM for another half a second. Now total displacement delta theta is simply the area on the 0 to 1 second of omega dt. So geometrically it's this area, this complete area here, which is the area of the triangle to the left plus the rectangle to the right. So you can figure out the total angular displacement simply. Now if the problem then goes on to saying what is the angular position of the object with respect to where it started, for example, initially. Now remember, 1 RPM brings the object back to the same angular, same position where it was before, so you need to subtract whole number of revolutions from whatever delta theta you have, and the remainder then gives you the by how much the final position is kind of separated in angular terms with respect to the initial position that the object had. Here's a problem involving an object which is moving on a surface around a circular path. The object, I believe this object is a rocket-powered hockey puck, something that is found in everybody's closet. So we have our object and it is rocket-powered, so there is an F thrust. F thrust is what is propelling the object in the forward direction, and the object, our rocket-powered hockey puck, is connected to the center of the circle via a string, a rope, the radius, so there is a T tension that is that is applied to the object, and that tension is what supplies or what provides the radial force to make the object move around in a circular path. So and there's of course friction force, and friction force Fk is the kinetic friction force, and it's in the reverse direction, in the negative tangential direction. So in solving circular motion problems, more than likely you will have to come up with two free body diagrams, one showing the RZ coordinates and another one showing the RT coordinates. So drawing the RZ coordinates for our object, here's the hockey puck. Our R is to the left, that corresponds with what we have on the picture. Z is to the top, of course. So the forces acting on the object are weight downwards and normal force from the surface upwards, and of course we have tension in the radial direction. So we can now go apply um, Newton's, let me see, there we go. We can now go apply Newton's equation in the z direction. In the z direction, as you know, the sum of the forces is equal to 0. Sum of the force in the z direction, looking at our free body diagram, is n minus w. That gives us n is equal to w. Now looking at the r direction in our free body diagram, the sum of the force in the r direction is equal to mar. Ar, as we'd seen before, Ar is equal to v squared over r, or r omega squared. These two are equivalent because, if you recall, v was equal to r omega. So Ar we can write as mr omega squared, and the only force in the r direction is T, and it's positive because it's pointing towards the positive of the r-axis. Now, taking the bird's eye view at our object and doing the RT or TR free body diagram, once again the object is at the origin, our R coordinate is again to the left, and in this case T is tangential to the circular path. This is our circular path here. So in the tangential direction we have the thrust force FTH and the friction force, which is in the negative t direction. And applying Newton's law, in this case the sum of the forces in the t direction is equal to mat. Now at is the tangential acceleration. That's the acceleration that either speeds up the circular motion, slows down the circular motion. Ar, the radial acceleration, results in a circular motion, and at either speeds it up or slows it down. And the two forces are the thrust force minus the friction force, kinetic friction force. Kinetic friction, as you know, is kinetic friction coefficient times the normal force. Let us substitute for normal force from this equation, and substituting W instead of N gives us F thrust minus mu K mg, which is equal to MAT. So rewriting these two equations, we end up with F thrust minus mu K mg from up here is equal to MAT. So that's an expression for MAT. And we know, I believe I gave this in the previous lecture, that AT is equal to R alpha. So we can then calculate what alpha is. So alpha is AT divided by R. And knowing this, you can now go ahead and use the kinematic equations of motion to solve, for example, how many revolutions, or what is the angular displacement that the object makes before reaching a certain velocity, etc., etc. So the key here was using the Newton's equation to come up with an expression for our angular acceleration, which then enables us to use the kinematic equations. Once again, the drill is the same as what we had for linear motion. You identify all forces, and then do a free body diagram to calculate the net force, or the sum of the forces in a particular direction, and that is equal to ma. Okay, so that gives you your acceleration, and then having acceleration, then you apply kinematic equations For linear motion, you apply the kinematic equations for linear motion. In this case, of course, we apply kinematic equations for circular motion. So equations like this, for example. In this problem, if we knew that the tension, there's a maximum tension before the string breaks, that is, the rocket of course provides a constant acceleration forward, so we expect our hockey puck to keep accelerating. However, there is a maximum tension that this string can withstand. So that maximum tension relates to a maximum angular velocity that the object can have before it breaks. So that maximum angular velocity then is equal to square root of maximum tension divided by mr. And where does this equation come from? This expression here comes directly, let me switch the color of my pen, comes directly from the analysis that we did a minute ago. So that gives us a relationship between tension and angular velocity. So we know that for a given angular velocity, the tension will have a maximum value, after which, as soon as the string breaks, of course there is no longer a tension being applied to the object, and the object would carry on a linear path. So now that we have an expression for maximum tension or maximum angular velocity, we use our kinematic equation. We have, oops, I'm sorry, I didn't mean to do that. So we have an expression for our angular acceleration, we have an expression for final angular velocity, assuming that we start from initial angular velocity of 0, then you can use this equation here to calculate how much angular displacement, or how many revolutions the object will go through before the string breaks, for example. This is an example of an object similar to the car example that we did. So let's say it's an object moving over a hill, and in the radial, if you do, I'm ignoring friction in this case, if you look at the RT free body diagram, we have W and N acting on the body. Your analysis is a simple one. Sum of the force in the radial direction is simply W minus N, which is equal to mv squared over r. Once again, AR is v squared over r. I apologize if I'm repeating myself too many times, but that's, I guess, how we learn. And once again, notice that in this case, since the object is at the top of the hill and the center of the circle is below it, I've chosen my r coordinate pointing downwards. That's where the object is, and the r coordinate points down. Substituting mg for w, I guess the question here is at what velocity, let's call it velocity critical, will the object leave the road. If you're traveling fast enough, then the car would leave the road, of course, and that leaving the road is when you lose contact with the road, and when you lose contact with the road, the normal force that the road exerts on the object becomes 0. So critical velocity occurs when normal force is 0. So substituting for substituting mg for w and 0 for n, we end up with this expression here. So our n is 0 because of this argument here. So at critical velocity, I set n to be 0, so now you can end up with a simple expression for this critical velocity, which is square root of rg, and noting that linear velocity is related to angular velocity via this expression, you can also come up with an expression for critical angular velocity, which is square root of g over r. So that's that's what we mean by critical velocity. That's when if you're talking about a car moving on a road, on a hill, that's when the car loses contact with the road. Or if you're talking about Ferris wheel with the passenger riding in one of the cars on the Ferris wheel, and at the top of the wheel, that's when the passenger would feel weightless. When normal force is 0, that's when the passenger would feel weightless. So if the Ferris wheel were going around at this critical angular velocity, that's when the passenger would feel weightless, because normal force would be 0. Here we have an example of an object, which let me show in green, of an object that is connected to a pole. Here's the pole via 2 rods. So there is rod 1 and rod 2. And the object is undergoing circular motion. If you look at it like this is a side view, so the object is moving in and out of the page, moving around in a circular path, where the blue line that I have on the drawing shows the radius of the circular path, with the blue dot, this here, being the center of the circular motion. So the plane of the motion is perpendicular to that of the page. So a free body diagram in this case, well, first of all, let's identify forces acting on the body. Well, of course, we have weight W acting downwards, and then we have tension 1 from the first rod and tension 2 from the second rod. And if you do a free body diagram, as I've shown here, let's look at the RZ coordinates. Once again, I've chosen R to the left because the center of the circle is to the left of my object, as depicted in the diagram. And our forces are, of course, weight T1 and T2. So the angles are given for the angles that T1 and T2 make with respect to the radial axis. They are both 30 degrees, so this baby here is 30 degrees, and that's 30 degrees as well. Doing a simple analysis, in the R direction, Newton says that sum of the force in the radial direction is mass times acceleration in the radial direction. And looking at our drawing, we have T2 cosine 30 plus T1 cosine 30 must equal MAR. Once again, AR is V squared over R. And you do a similar analysis in the Z direction. FZ, which we know must equal 0, is given by T2 sine 30 minus T1 sine 30 minus mg. So that's the Z component of T1, Z component of T2, and W here, and all that must equal to 0. So now you can go and do your algebra to, for example, figure out what the if you know the angles, if you know the mass, what the tensions in each rod is, for example. That's a fairly simple algebra to conclude such a problem. Slightly more involved problem is shown here. What we have is an inverted cone, and we have a ball which is moving around in that blue circular path inside the cone. we know the radius of the base of the cone and the height of the cone, and the problem is asking us to come up with an expression for the linear velocity in terms of the radius and the height y, the radius of the circular path and the height y that the ball is rotating at. So to do that, let me draw this line here. So this is onto the center here, and let's say this angle is theta. All right, and my RTZ coordinates is shifted a little bit, so let me, oops, I'm sorry, I didn't mean to do that. So let me move the RTZ coordinates a little bit. Probably simpler done like this. So let me just draw this line here. Let's say this angle is theta, and I can show my RTZ coordinates as, well, the R coordinate is towards the center, so this is R. Then I have T coordinate, which is tangential to the circle, and of course Z pointing up. Okay, so that's the RTZ coordinates that I have. Drawing the and let's come up with an expression for this angle theta. Looking at the drawing that we have, this is A, of course, and this height is H, so tan theta is A over H. Or for the ball in motion, tan theta is also equal to R, which is the radius of the circular path, divided by Y. So you can show that this is true by just looking at the drawing here. Now, if I now do a second drawing, which shows kind of just a section of the cone, my object is of course here. The forces acting on the object are the weight W acting directly down and the normal force from the wall. Okay. Now my RTZ coordinates, I have not shown the T coordinate because I'm going to ignore friction forces for the time being. So let's just focus on the RZ coordinates. If we just look at the RZ coordinates, the only force contributing to the radial force, which will result in a radial acceleration, is the normal force from the wall. So NR, which is the radial component of the normal force, which is given by n cosine theta, all right, that's the force that is going to contribute to the well, that's the only force in the radial direction. So doing our Newton's analysis, we have the sum of the force in the radial direction is equal to NR, which is n cosine theta, and that must equal mv squared over r. Remember, this is AR, MAR. Okay, so we end up with an expression like this: n cosine theta is equal to mv squared over r. Now looking at the z component, what do we have in the z component? Well, we have the t component, the tangential component of n minus w, and the tangential component is n sine theta, and w of course is mg, which gives us n sine theta must equal mg. So taking this equation and the equation that we just derived, and dividing equation 1 by equation 2, so if I divide equation 1, equation 2, I end up with tan theta is equal to gr over v squared, but tan theta, we had said a minute ago up here that tan theta was a over h or r over y, so tan theta. Substituting a over h for tan theta, we end up with a over h is equal to grv squared, or v is equal to square root of g r h over a, if I didn't make any mistake. Okay, so that's the expression for the linear speed of the object in terms of the height and the radius of the cone. And so that's one expression. Now you can also turn this expression around and write it for how high, that's in terms of y, how high the object will move in a circular path for a given speed. So you can turn it to an expression in terms of y if you wish. So I'll leave that exercise for you to complete. So just to recap, circular motion. We define circular motion as an object mass m moving around in a circular path with radius r. Let's say in our coordinate system, the xy coordinate system, the object's initial position is defined by an angular position, initial angular position theta I, and if it were to move to a final angular position, let's call that theta f. Notice that both angles are measured with respect to the same coordinate. Then the angular displacement delta theta is simply theta final minus theta I. If the object were to move to make this angular displacement in time delta t, then the object's angular velocity omega is simply delta theta divided by delta t. And if you use radians to measure delta theta, then the linear displacement of the object is arc length delta s. Delta s is simply r times delta theta. Okay, and differentiating this expression with respect to time, we ended up with linear velocity is equal to r omega. Right, and we also showed that there must be an a radial acceleration acting on the object to maintain it moving in a circular path. The radial acceleration is one that points towards the center of the circle at all times, and the magnitude of the radial acceleration is given by the speed of the object squared divided by r, which you can also write as r omega squared because of this relationship up here. And if there is also a tangential acceleration acting on the object, then the total net acceleration, of course, is the vector sum of ar plus at, where the magnitude of a is given by the Pythagorean relationship, ar squared plus at squared, and the angle that a makes with respect to the x-axis is given by arctan of at over ar. And at rather, is what gives rise to an object winding down or winding up, an object undergoing circular motion speeding up or slowing down, and at is given by r alpha, where alpha we said is the angular acceleration, whose units are radians per second squared. Now the units for at, of course, are meters per second squared, because that's the linear acceleration we're talking about. So going back, the units for omega were radians per second. These are the units for omega, of course, just a reminder. And the kinematic equations of circular motions are similar to those for linear motion. and they're given as final angular velocity is equal to initial angular velocity plus angular acceleration times delta t. Final angular position is equal to initial angular position plus initial angular velocity times delta t plus 1/2 of alpha delta t squared, and angular velocity squared is equal to angular velocity initial squared plus twice alpha delta theta. So these are valid only and only when alpha is constant. Okay, and you can also apply Newton's laws when you do your free body diagram. Work out the net forces in the r direction. That must equal mass times acceleration in the r direction, which is equal to mr omega squared, or mv squared over r. Now the sum of the forces along the tangential direction is equal to mass times at, right? And for uniform circular motion, of course at is 0, therefore sum of the forces in the tangential direction are also is also 0. Now along the z direction, just remember that whether we're talking about uniform or non-uniform, Fc is always equal to the net force along the z direction is always equal to 0. And just like the case for linear motion, you can use the graphic analysis tools that we learned about. That is, if you have a plot of angular position, let's say in radians, versus time in seconds, and it looks like, let's say like this, right? Now the slope, working out the slope of the lines, each section gives us our angular velocity, that's radians per second. So in this section we have a positive slope, it's a straight line, so it's a constant positive value, like this. That's for this section right there. For the second section, it's a 0 slope, so angular velocity is 0. And here it's a negative slope, so it's a negative number, but steeper slope, so it's something like this. Okay. Now, as far as if you were to then calculate the angular acceleration, of course you take yet another derivative, d by dt of omega, to work out angular acceleration for the objects. In this case it's what we have, of course, angular acceleration in radians per second squared. We have 0 acceleration, and then there is a burst of negative acceleration. That's what brings the object to constant angular velocity. Then it continues at 0 acceleration until there is a big burst of a positive angular acceleration, and it continues at that rate moving forward. So if you're interested in figuring out change in, let's say, change in angular position, then you simply look at area under the curve between Ti and Tf of the velocity, angular velocity curve, and change in angular velocity is simply Ti Tf of alpha dt. So everything that we learned for linear motion applies in the case of circular motion as well. And the other thing to remember is that anything which is an object which is moving in the clockwise direction has a negative angular velocity, angular displacement, etc., and an object moving counterclockwise is denoted as having a positive angular velocity. So an object which is moving around in a circular motion in the counterclockwise direction. So if omega, that means omega is positive. If it has a negative angular acceleration, that means the object is slowing down. Alright, if it's moving clockwise, that's negative omega, and a negative acceleration, that means speeding up. Speeding up, or actually more correct is winding down and winding up. If an object has a negative angular velocity and positive acceleration, that's also winding down, and a negative and a positive angular velocity and a positive angular acceleration, that's winding up, of course. Okay. I guess that's about it for this chapter. So let me see if there is anything else I wanted to share with you. Perhaps I can do one last example of the graphic analysis technique, and that is, let's say I'm just going to make up a problem. I hope it makes sense. Let's say we have an object which is which starts at rest, and then winds up to let's say 1000 RPM in 5 seconds, and then winds down to 5000 RPM in 10 seconds. Alright, so what is the displacement of the object? Well, let's just go ahead and plot the graphs here. So plotting angular velocity, in this case RPM, in revolutions per minute, versus time. So this is our 5000 value, this is our 10, I'm sorry, this should be, I said winds down to 5000, I meant 500, I apologize. So we have 500 here and we have 1000 here. So our object starts at rest, it winds up to a value of 1000 in, let's say, 5 seconds. This is in seconds. And then winds down to 500 in twice the time. So it winds down like that, right? So what to get the acceleration plot, angular acceleration, in this case it will be RPM per second. What we'll end up with is, this is time versus seconds again. What we have here is the slope of this line, which is 200. So this would be 200 RPM per second acceleration, angular acceleration. And then for the second half we have, so this is 15, so we have, what did I have here, 205 seconds, that's 10 seconds. We have 50 divided by, I'm sorry, yeah, 500 divided by 10, which is 50, which is negative 50 RPM. Alright, so the slope here is 200 RPM per second, and the slope of the line here, well, that's negative to start with. Also, the slope is 1000 minus 500, which is 500. It takes place over 10 seconds, so that's negative 50. So that's the slope of the line there. So if you wanted to, for example, figure out the change in the velocity, angular velocity, change in the angular velocity of the object between, let's say, 10 seconds and 15 seconds. Alright, that's simply the area under 5 seconds, I'm sorry, 10 seconds to 15 seconds of the angular acceleration versus time plot. And what we have here is from 10 seconds, which is from here to there, so our delta t is 5 seconds, and our height is negative 50, so negative 50 RPM per second times 5 seconds, that's negative 250 RPM. Okay, so negative 250 RPM is the change in the angular velocity that the object experiences from 10 seconds to 15 seconds. Since I'd given you the information before, of course this makes it obvious, but had you been given the acceleration information without given the initial information and asked to find the change in angular velocity, that's how you would have gone around and gone to attempt to figure it out. So and similarly, if you're interested in figuring out the total angular displacement over a certain time, then you use the area under the angular velocity versus time plot. So angular displacement between 0 and 5 seconds, for example, is simply the area under 0 to 5 seconds of omega dt, and what we have here is 1000 RPM now times 5 seconds. Okay, now here is something you need to be careful of, and what we have here is we're mixing units. We have revolutions per minute and we have seconds. So what you need to do is convert RPM to revolutions per second, and to do that you simply divide it by 60. There are 60 seconds in a minute, so that's 1000 revolutions per second. Well, if you divide 1000 by 60, that is times 5 seconds. Now you can go ahead and multiply it, so whatever 5000 divided by 60 is, then you can get a number in a number of revolutions, which is relates to angular displacement. So take care to not mix minutes and seconds. In this example, in the first example that I didn't pay attention to that because the second here and the second down here cancelled out. I only ended up with RPM, which is what the problem was after. How many RPM did it go through? But here, because I'm multiplying seconds with angular velocity, I have to make sure that my units match. If I'm talking revolutions per minute, then I need to multiply it by time as measured in minutes. If I'm multiplying in time as measured in seconds, then I need to convert my angular velocity to revolutions per second, etc. Okay? Well, that's all, folks. Thank you.